Okay, welcome to the Chapter 7 homework. We are going to be going through this right now. The first thing I'm going to do here is read the question. The population has a mean of 29, so mu is equal to 129. And they're giving me this sample of 8 items. And let's get rid by these. And in order to find what the sampling error is going to be, again, sampling error is x bar minus mu. So I have to find what x bar is. X bar is simply the average of the sample. So if it's x bar minus mu, 131 minus 129, is that 2.805. You can definitely have a negative sampling error, and that would be, obviously when mu is larger than x bar. So if you do get a negative, make sure you're indicating that. Okay, let's go to the next problem. Okay, so the air temperature is measured every 6 hours for 1 week. Let's go ahead and grab this. I'm going to go ahead and copy it to the clipboard. And we're going to be using a systematic sample to grab the 4 temperatures that we need. So in this case, they're actually asking us where n is equal to 4. We have to find from this sample what k is equal to. Remember that k is equal to big N over little n. And if I know what big N is, go down here, it's looking like it's 28. Okay, so if I know that big N is equal to 28, I can figure out what k is going to be. And remember that k is for every kth value, we will compile a sample from those values, okay? So in this case, if I need 4 temperatures, I have to take that 28 and divide it by the 4. So this essentially means that I'm going to take every 7th value from this data set and create a value comprised of 4 values. Create a sample, comprised of 4 values, okay? So here I'm going to take the average of 7, 14, 21, and 28, okay? And that's giving me my x bar, where n is equal to 4. Okay, so don't confuse n with k. Little n is the size of the sample, and k is how we're going to go through and select the values to compile our sample statistics, okay, and comprise the different subsamples from that population. Okay, so in this particular case, we're going to calculate the sampling error for the sample. So remember, this is x bar. I need to find mu. If I have this entire population, mu is going to be equal to average of all of these. Okay, so this is mu, this is x bar. In order to figure out what the sampling error is going to be, equals this minus mu, x bar minus mu, and this is the sampling error when n equals 4. Okay, so that's how we're getting that negative 0.50, and it's telling me to round to 2 decimal places, so I go ahead and do that. All right, now we're getting another one to draw a systematic sample consisting of 7 temperatures. So instead of 4 here, we're actually going to go ahead and change this to be 7. Okay, so in this case, my new k is going to be equals, my big N is still the same, 28, And here I'm going to divide it by 7, okay, in order to get what that value of k is going to be. So here what this is saying is that for every 4th value, I'm going to need to collect that to comprise this new sample. Okay, so let's go equals average and go through every 4th. 4, 8, 12, 16, 20, 24, and sorry, put on here, and got 28. Okay. Just make sure I grabbed all those correctly. Good. Okay, so this is my average, and again, x bar when n is equal to 7, right? Again, getting the sampling error is x bar minus mu, and that's giving me that negative 6.38 degrees Fahrenheit. Now here, it looks like I skipped over the first one because I had not drawn this down, so we'll just do this quickly. Let me pull this down here, where n is equal to 2. So where n is equal to 2, it's actually going to be 28 divided by 2, which is going to be 14. So we're going to take every 14th value here to get our average. And that is going to give us 14 and 8. Okay, so this is going to give us a sampling error. Is that 2.82. Okay, so this is the sampling error when n is equal to 2. Okay, so what we're actually seeing here, if you look at this sampling error, at first going from n to equals 2 to n to 4, it does go down initially. It reduces, but then it spikes back up to the largest absolute value when we have a larger sample. And that is actually counter to what we would expect. We would expect as our sample increases, the sampling error to go down, because recall, here's your entire population. If I have a small sample, the distance between the sample and the population is large, but as that sample becomes bigger, that space reduces, okay, or the error reduces, the difference between the sample and the population reduces. So the sampling error is going to go down. In this case, that is not happening, and so you have to sort of think about why that might be the case. So here we would say, in general, increasing the sample size, it makes the magnitude of the sampling error smaller, and the sample does not tend to follow that. And it could be, specifically because we're looking at temperature, that there's some periodicity in the data that could definitely impact the sample that specifically as it is shown in Part C. So every 6 hours, it could be, there's pretty stark differences every 6 hours. If you're going through sort of the night, it might get, you know, depending on where you're living, it might get significantly colder. Okay. Let's go to the next one. And for this one, we have a population of 300, okay, and a mean of 55, standard deviation of 21. What's the probability of a sample mean 57 or less from a sample of 45? Okay, so here they're actually telling us, they're giving us a hint when they tell us, consider a population of 300. That tells me that there's a big N involved, and when I see any big N that's given, I know it's a finite population. And so we're going to have to apply the finite population correction factor. N So essentially here, if we know what the population is, and they're telling us what the mean of that population is, that's actually mu. So mu is 55, and standard deviation is actually our sigma, as opposed to s, small s or SD, and that's equal to 21. Okay, so before we even go down the road of figuring out what the z-score is and figuring out what the probability of that z-score is, we're going to need to calculate the adjusted standard error. Okay, so the standard error of x bar, here I'm going to actually write these down, and let's say x bar here. Now here, this is what, I'm just going to use this throughout this homework as an indicator of the standard error of the mean. And this I'm going to use as the standard error of the mean that's adjusted for the finite population correction factor. So remember that x bar, the standard error of x bar of the mean, is simply the standard error divided by the square root of small n. And in this case, we have a small n of 45. Okay. Okay, so now I have my sigma x bar, which is the standard error. Recall, whenever I have a standard or a problem where I'm trying to figure out the probability of something happening, and I have the exact number of people that are, or observations that are in the population, I have to adjust it for it being a finite population. So the finite population correction factor is given by the square root of big N minus little n divided by big N minus 1. Let's make sure this is correct. Good. And then what I end up having to do is adjust the standard error of the mean by that finite population correction factor, and I just multiply those two together to get that adjusted value. Okay, so we go from a standard error of the mean of 3.131 or 3.130 to a standard error of the mean adjusted to about 2.891. Okay, so it's a smaller standard error. And when I'm calculating my z, I kind of try to put a note in here. Remember, that's the numerator is x minus mu, and your denominator for the z is the standard error of the mean adjusted. Okay, so this value. So here it's telling me what the value is that we're interested in, and the x is less than or equal to 57, so it's going to be that 57 minus our mu is 55, and we're dividing that by the standard error of the mean adjusted. So again, here what we're interested in is the probability of a z that is less than or equal to 0.6918. So it's falling in, if I'm looking at it from the perspective of the normal curve, it's definitely above the mean, so we know that the probability is going to be greater than 50%. And at the same time, it's not, entire standard deviation above. It's about 0.7. Okay, standard deviation is above the mean. So how do we get that probability? It's that norm S distribution, plug in the z, and in this case, we're interested in the probability of it being that value or anything below it. So that makes sense. It's about a 76% chance. Okay, and we know that because it's definitely going to be above 50% because the z-score is positive. If you have a z-score, recall of 0, it's going to be right at the average, the mean. Okay, so the tricky part about this problem is just applying that finite population correction formula. But if you had it set up, this should definitely be a clue. It says consider a population. That should ring bells. You should see flashing lights that say finite population correction factor. I got this. Okay, good. Let's go to the next question. Okay, according to a research institution, the average hotel price in a certain year was 90.75. All right, so that's mu, the average, right? And we've got our mu here. Of 90.75. And the standard deviation is, again, sigma, and that is telling us it's about $15. A random sample of 50 hotels was selected. Here they're actually not giving us the population size, so we are not going to have to apply the population, the finite population correction factor, but it's looking like we need to definitely calculate some probabilities. So the first step to doing that is of course the standard error of the mean here. Okay, so the standard error of the mean, I'm going to just use this. This is nice to just pop this in here. Okay. So again, that's just simply, if you recall, this sigma x bar. So the x bar is just the x with a bar over it. I can't do that on this old computer that I have at my house. So, all right, so the standard error of the mean is again given by sigma divided by the square root of little n. Okay, so this is the standard error of the mean, 2.12, and we see that here. Now, what's the probability of the sample mean being less than 92? Okay, so what we first have to do, the probability that x is less than 92, we're saying x bar. Okay, if we know that the population average mu is 90.75 with a standard deviation of 15, I'm grabbing 50 hotels and I calculate their average. What's the probability that it's going to be less than or equal to 92, given that I know what the actual population parameter is? So the first thing we have to do is convert this to a z-score. Okay, so what's the z where x is equal to 92? 92 minus mu divided by sigma x bar. So obviously a little higher than the mean, so it's going to be positive. Now that again is the z. If I want to find the probability of that z, it's given by that. Okay, so what we're doing here is saying what's the probability that the z is less than or equal to 0.589256. Okay, and that's how I'm getting that 0.7222. First, I convert this 92 into a z, and then I find the probability of that value, of that z value, given the normal distribution, the standard normal distribution. All right, let's go to the next one. The probability of the sample B will be more than 94. More than 94 is going to signal to me that I need to use a complement. And so I'm going to take 1 minus whatever the probability of that z is, because the z, again, the probability is listed in the tables, and you know, in Excel it gives you the cumulative probability of that point and everything that falls below it. Okay, so the probability that x is greater than 94. Let's see what that is. 94 minus this mu divided by this. Okay, so this is a z where x is equal to 94. Okay, it's way above the mean, 1.5 standard deviations above the mean, and we're going to find the probability of this particular value. And what that's going to give me is everything that falls at that value and everything below it. So we have to take the complement of it. I'm going to do that all in one step here. Okay, and that's where I'm getting at 0.0628. This is the probability of 1 minus the probability of z is less than or equal to 94. And the probability that z is less than or equal to 94 is going to be, again, corresponding to the z of 1.53. It's going to be pretty high, about 90.94. Okay, equals, let's see, the probability will be between 90 and 91. When we see a between, what we're going to end up doing is take the probability, find the z's of those two corresponding values, find the probability, and then take the difference between them. So let's just find it for, it's looking like between 90 and 91. So we'll find the z where x is equal to 90. 90 minus this divided by this. Okay. And let's just grab the probability of this quickly. Get the cumulative probability of both of these. 91 minus 90.75 divided by this, and equals this to get our two probabilities. And then I'm going to take this probability and from it subtract the smaller probability, and that's what's giving me about 0.851. And again, what this is essentially corresponding to, if we're thinking about it from the perspective of the normal distribution, the normal distribution is essentially, if we have, let's see, I'm trying to figure out the best way to illustrate this without having the ability to draw it. You see it like this. The smaller value of x90, we're going to take that, and then we take the larger value of 91 and get all the way to there, and to find the area in between, it's right, you take the difference between those. Okay. Okay, a college has 260 full-time employees that are currently covered under the school's health plan. Again, alerts, alerts. This is telling me there's 260 people in this population. Here what I've done is I've filled in all of the necessary information. We have a big N, we have mu, an average from our population, sigma, we have little n, and now because I know I have a big N, I know I have to apply a finite population correction factor, which is again given by the square root of big N minus little n over big N minus 1. Sigma x bar is given to us by the sigma divided by the square root of little n. And then when I need to adjust it, I'm multiplying that sigma x bar, the standard error of the mean, by the finite population correction factor. Okay, so that's giving me that standard error adjusted. Okay, that's how I'm getting the standard error of the mean there. It's not going to say standard error of the mean adjusted. That's the term that I use. And it's again adjusted for a finite population. All right, so that's what we're going to be using in our z-score when we're figuring out what the probability of, in this case, that x will be less than 1815. Okay, so let's first calculate what that z would be. 1815 minus mu 1880 divided by our standard error adjusted. Okay, so that's less than the population mean, and the probability of this being this z-score or anything below it is about 0.2070. Okay, so this is the probability. This is the same thing. The probability that x is less than 1815 is the same thing as saying that z is less than or equal to negative 0.81. I don't know. Oh, okay. Put this out. These two are saying the same thing, given all of this information. Okay. All right, this probability that the sample is going to be more than 1860. First finding the z-score associated with that using the standard error of the mean adjusted. Finding the probability of that and everything below it. Here it's asking me though what the probability of being more than that value is. So I'm going to take this entire thing and subtract it from 1. And that's where I'm getting that 0.5992. So probability that in this case z is greater than negative 0.25138. Okay, and again that's the same thing as saying the probability that it's greater than 1,860. The probability that it's between 1895 and 1930. Again, what we're doing here is finding the respective probabilities for those using the different z's in the normal distribution. Okay, and here 1930 minus this divided by this, and this. Okay, and so I'm going to subtract this from this. All right, this is the probability that x is equal, or the z associated with this. The z where x equals 1895. So the z where x equals 1930. Okay, so because 1930, if you look at it again as the curve, 1930 is up here, and 1895 is like here. So if we find the cumulative that goes all the way to the bottom and take the difference between those, it's going to give us that area in between. So let's take the difference between these probabilities, not the z's, the corresponding probabilities with those z's, 0.1604. Good. Right, this data table contains frequency distribution of the heights of the players in a basketball league. It may be a little misleading, but this is actually a population because it's a league. Okay, so population, plagues, finite population correction factor. Okay, so I'm just gonna lay it out there. We know here you don't find out what the small n is until a little later. Part B, 45 players. The population mean is given by this, and we see at the bottom that we've got 60 players in this particular league. Okay, so this is, let's do this. This is mu. And that's 70.1. The population standard deviation, okay, if we do this, that's going to give us the, in this case, thinking back to our Excel formulas, equals standard deviation dot p. It's of this population. Okay, it's going to be that 4.86. Recall now, because this is a finite population, and it's kind of pushing it at you here, the first two parts of the problem. Population being the population standard deviation. So now when they're asking us the probability, we have to immediately apply to our standard error of the mean that finite population correction factor. So standard error of the mean, just going to grab it from here, the adjusted one. So sigma x bar is given to us by sigma divided by the square root of n, which they're telling us is 45 here. Okay, let's get rid of these. Finite population correction factor equals the square root of big N minus little n. Big N is 60, little n is 45. In this particular problem, and you divide that by 60 minus 1, or big N minus 1, and take the square root of that entire fraction. Then multiply these two together. Finite population correction factor and sigma x bar. That's going to be our denominator when we're calculating our z-scores. Okay, so here they're saying for part B, the probability of the sample mean will be less than this. Okay, so probability that x will be less than or equal to 69.5. All right, first thing I do, find that z, 69.5 minus the actual mu divided by my standard error of the mean adjusted. This is my z, okay? So I'm actually going to pull this over here. So this is the z-score. Now find the probability of that z-score being given by norm as this. In this case, it is true. We want the probability that it's less than or equal to that. Okay, so the probability that z is less than or equal to, in this case, negative 1.64352. So you go and say to that. Right. I'm not going to write this out because it could be that they want us to say what the probability of it is more than it. Okay, so in this case, with the probability of it more than 71, let's first find the z. 71 minus 70.1 divided by standard error of the mean adjusted. And because they're saying more than, again, I'm taking, let's find the probability of that z, the cumulative probability, and take that entire thing, because that's, again, we're looking at it from a curve. If we're looking at here, it's everything that falls below it. I'm interested in what's up here. So I have to take, and I know this entire area is equal to 1. So if I know this area, and I know this entire area, I know this area. 1 minus, that's at 0.0068. And next, we're looking at the probability of it being between two values, equals 70 minus this divided by this, and let's do 71.5 minus this divided by this. And we can find the area in between here now. Okay, so equals this. This is going to be about 0.6079. Okay, good. All right, so for this problem, again, it's not very clear that it's a finite population correction factor, but it's giving you, alluding to it because it's saying with the population is here. So you have to kind of infer that you need to apply that population correction factor. Okay, here, for a population with a proportion equal to 0.35, so P equals 0.35, and calculate the standard error of the proportion for the following sizes. So the standard error of the proportion, let me just, okay, so sort of like this. This would be kind of a sub. It's really hard not to have right equipment here. Sigma x, or yeah, sigma p you're actually going to divide this by n. I'm going to set it up though, so we can just simply drag this down. And here I'll put this 4, 5 in now though. So I'll do 45, 90, and 135. I'm going to copy this. And here I'm going to reference in my denominator, I'm going to reference this. Recall that B1 though should be an absolute reference, right? Because if I drag this down, I can do it in either the formula bar or right there in the cell. When I drag this down, I want the B1 to stay the same, okay? So we see this 0.0711 here, 0.0503, and 0.0411. And again, the formula for that is P times Q over N, and take the square root of that. Okay, so the square root of the fraction, wherein the fraction on the top is P times 1 minus P, or P times Q, because Q is equal to 1 minus P, and divide that by the sample size, and take the square root of that. Okay. Okay. A social media survey found that 65% of parents are friends with their children on a certain online networking site. Like, I'll put this in quotes, friends. A random sample of 150 parents was selected. Complete parts A through D below. Okay, so here we know that P is 0.65 and a random sample of N is 150. So calculate the standard error of the proportion. Again, that's given to me this equals the square root of this times 1 minus this divided by this, and at 0.0389. Now, what's the probability that 105 or more parents from the sample are friends with their children? Okay, so they're interested in figuring out P hat. And P hat is like the estimate of the proportion. Okay, so the probability 105 or more parents from this site are friends if they sampled 150. Okay, so this is essentially like saying we have X bar as our mean. P hat is the estimate for the proportion, whereas x bar is the estimate of the mean or the average for the sample. Okay, so p hat here, 105, we have to calculate what 105 out of 150 is. So don't forget to do that. That's your first part, is that p hat is 0.7. And we're going to then take that 0.7 and calculate the z-score, where instead of x bar minus mu in the numerator, it's p hat minus p, and then the standard error of the proportion in the denominator to get our z-score there. And that's at sigma p here. Okay, so this is actually 1.28 standard deviations above the mean under the standard normal distribution. Let's see what the probability of that is going to be. Oops, I think I misspelled true there. And here, recall, it's saying what's the probability that 105 or more parents from the sample are friends. Okay, so or more, we have to take that complement 1 minus that entire distribution or probability. Okay, so this is our part B. Now let's go to part C. What's the probability that between 98 and 107 parents from the sample are friends? So we're going to have to find two different p hats here. P hat 1 is going to be 98. Well, let's find the z actually while we're just in it. 98 divided by 150, and the z, this minus this divided by this, and let's do it all. Okay, now let's do p hat 2, which is going to be equal to 107 out of 150. The standard normal distribution. And recall, whenever they're saying that between, so the probability that something is between it is going to be this minus this, that 0.1439. So this is the probability that between 98 and 107. So the first thing we have to do there, again, convert both 98 and 107. P hat 98, P hat 107. Convert both of those to proportions. Put those respective proportions into a z formula where it's p hat minus p divided by the standard error of p, and then find the standard normal distribution probability. Then take the difference between those two probabilities. Okay, this last problem in this particular one, part D, if 84 parents responded that they are friends with their children on this networking site, does this result support the findings of the social media study? So the social media study said that 65% of parents are friends. Okay, so if we only found 84 out of our 150 people that we surveyed, 84, that's only a p hat of 0.56. What we're trying to determine here is if this 0.56 is close enough to the reported proportion that we would accept it in the normal realm of possibilities, that it's like, yeah, give or take. This 0.56 is seemingly way off, so we can actually calculate the probability that if we can accept this proportion as truth, 0.65, that's actually the parameter. There are going to be a certain range of values that we would accept within that are not exactly equal to 0.65. And we can calculate if 0.56 falls within that realm of possibilities simply by calculating our z. Okay, so if we state that 0.65 is actual truth, the probability of 0.56 falling within that essentially confidence interval, and we'll talk a little bit about that in chapter 8. This 0.56 is associated with a z-score of negative 2.311 about. And so we can calculate with the probability of a z-score that's small, essentially. And it's less than 1 or 2% of the time is if this 65 is actually the true value, less than 1% of the time 0.56 is going to fall within that bracket, if you will. Okay, so if you look at these questions, the only two that are going to pop out and you can deduce as being, you know, runners in the final answer are the ones that begin with no. Okay, so the probability of obtaining a result that is that small, 0.56, that's much smaller than the given proportion, are that being accurate is less than 0.05. And we talk a little bit about alpha, setting that to 0.05 if we want to have a 95% confidence interval. And again, we'll touch on that in chapter 8. But 0.05 is usually, you know, less than 5% of the time this is going to be the case. And in this case, it's actually, you know, about 1% of the time. So that's the last answer. Not that you get a probability that is greater than 0.05, then you would say yes, okay, that the probability of giving that much, it does fall within the realm of possibilities. Okay, let's go to the next one. According to a national study, 35% of taxpayers use computer software to do their taxes for a certain tax year. A sample was selected. Let's calculate parts A through D below. Okay, so we've got our P, 0.35. We've got a little n of 145. And they want us to calculate the standard error of the proportion. The parameter actually for the proportion is pi. So in your text, it may actually state that. And that's obviously different than the constant pi. Okay, so sigma here is going to be given by the square root of this times 1 minus this. 0.0396. What's the probability that less than 33% used? Here we're gonna again 0.33 minus 0.35, divide that. I have standard error of the proportion. That's giving me my z, and I can find the probability that is associated with that z. Here, it's about 31% of the time, 0.3068. So here I'm just going to put P. P is less than 0.33. Okay, and P between 0.30 and 0.41. 0.30 here. And again, because of between, we are going to take the difference between these two probabilities. Okay. And this probability and this probability is at 0.8317. So what is the impact of changing the sample to 245 taxpayers? What does it have on the result? If you've set it up like this, you can actually just change this 245. And so watch what it does to the standard error of the proportion. 0.03961, if I put this up to 245, it makes it go down, right? So it reduces the standard error. And that allows the probabilities of the sample proportion are going to be closer to the population proportion, okay? So again, the probability that the sample proportions will be closer to the population proportion is a result of the standard error being reduced, and the reason driving that is the increase in the sample size. Okay. Okay. Club has 375 members. Population. Population alert. Okay, Golf Club 375. So Big N 375. Historical records show that probability is 0.34. Okay, so I'm going to make a big P here, 0.34. That's the estimated proportion, and a little n of 100. Okay, calculate the standard error of the proportion. But first, before I do that, let's calculate the finite population correction factor, because I know I'm going to have to apply that to the standard error. Big N minus little n divided by big N minus 1, and take the square root of that. The sigma p, standard error of the proportion, square root of p times 1 minus p divided by little n, and this adjusted. That's giving me that 0.0406. So now we have the adjusted standard error of the proportion. I use that in my z-score to calculate what the probability of these different p-hats are. Okay, so the probability that 28 or more members from the sample use the course at least once. So here we actually, remember, 28 isn't, we have to divide that into the sample size to get our p-hat. Fortunately, the sample size here is 100, so we can find the z of 0.28 minus 0.34 divided by the adjusted, and then find the here, and the probability that 28 or more members. Okay, so if I have an or more there, or more than, remember it's going to be 1 minus that. Okay, so given that there's 34 out of 100 people that we know play, what's the probability that 28 or more are going to play on average? It's obviously going to be high, around 93% here. The probability that between 30, so p 0.3, between 0.3 and 0.4. Let's find 0.3 first. Okay. 0.4 minus 0.34 divided by this equals 1s. Here. I forgot to do my true at the end. True. And again, let's find the difference. This is the probability that it's 40 or anything below. This is the probability that it's 30 or anything below. And that's giving me that 0.7678. So this last part is asking me 45 members from the sample. Okay, so let's find the z of that probability that it's equal to 45. Okay, I'll just say that. Or more. You can think about this 45 as being or more. It's higher than this 34%. So if they say, oh, it's not 34%, it's actually 45%, well, the probability of it being that or anything above it is going to be given by, first find the z, then find above it 1 minus norm Estes. It's very, very small. That would actually be the case. Again, that 0.45 or anything above it is actually falling within the realm of possibilities when the known population proportion is closer to 0.34. And so no, since this probability of obtaining a result this large or larger is 0.003, you actually have to put the value in there and put it into 4 decimal places. Given that historical records give an accurate estimate of course usage. So if you found a value that, let's say, well, if they actually found, let's say, like 20 people, okay, then you would calculate what the probability of that 20 would be if we know that the population proportion is actually closer to 0.30, but I'm just going to illustrate something here. Here, this equals norm Estes here. Okay. And so since this is a negative z-score, the interpretation would be no, because the probability of attaining a result this small or smaller, okay, it's a negative z compared to the known parameter, okay? Here we're saying, because it's a positive z, you're saying no, the probability of attaining of this result larger than this, okay, is 0.0034, okay? So I just wanted to show you that how the interpretation would look. And again, we're kind of looking for whether or not this probability is less than 0.05. And it definitely is. Okay. All right, at a certain college, 50% of employees carry dependent family members on their health insurance plans. Okay, so we know that P is equal to 0.57, and currently there are 175 employees working for the college. Dun, dun. Big N is 175. And here they're saying a little n is 60. Okay, so finite population, correction factor. Let's just do it quickly. Big N minus little n at the top and divided by big N minus 1. Okay, and the sigma P is the square root of this and 1 minus this divided by little n, sorry, 60. Okay. Now we have to multiply these together and find our z's. Less than 62% carry. Okay, so 0.62 minus 0.57 divided by standard error of the population. proportion adjusted equals norm Estes here, true. This is going to be close to 0.8320. Okay. Looks like some of my answers didn't save from yesterday. That's okay. Answer question in part using sample sizes of 150. Explain the difference in those probabilities. Okay, this is actually nice that I've set this up like this. So let's just bring this here and here. Okay, so here we've got, this is our z and the probability of that z, okay? Now once I change this to 100, obviously the z goes way up and the probability that z goes up. Let's change this to 150 now. The probability for a size of 100 is now closer to 0.9380. It's the beauty of having a beautiful Excel workbook that you will all have for your exams and your quizzes as a result of doing this homework. Okay, check this answer. All right, so let's explain this. Increasing the sample size does what to the standard error? If we're looking at the standard error, it's going down, right? The adjusted is going down too. So let's see one that decreases or reduces. And this in turn increases the probabilities that the sample proportions will be closer, right? So it's, as the standard error goes up, the matches tend to be more accurate. All right, answer the question in part A without the finite population correction formula. All right, so if we just took this out, this is part A here. If I simply took this out and made it, we'll multiply it by 1, okay? Now what's happening is the probability is going down to, oops, didn't mean to do that, 0.7830. The probability. And without the population correction factor, it seems to be that the standard error is definitely overestimated. Okay, it's not properly adjusted for it being a small, a finite population. Recall that the central limit theorem and population and sampling theory assume the population is infinite. Okay, so it's overestimated. And it causes the probability to be underestimated. Over, causing the probability to be under. Okay. Let's do this last one. Managers at a local phone service wireless retail center have a goal that 0.77 of the center's customers will be waiting. Okay, so their P, they're saying, is 0.77. We'll wait less than 5 minutes for service. So the data below shows the wait times of a random sample of 25 customers in minutes. Okay, so here we've got a little n of 25. And here we're actually going to grab the data. And we have to see how many of these are less than 5 minutes. So equals count if this is less than 5.0. Okay, so after I put these in here, I actually have to use the COUNTIF function. Greater than 5. I'm going to put 0.0 because if there's anything here, okay, so here what I'm actually going to do, I'm going to apply a COUNTIF. Greater than or equal to 5. Actually, I'll do less than. Here what I'm going to do is apply a COUNTIF function for these values and determine which are less than or equal to 5.0. Close that out. And 17. So what is that proportion? Equals 17 out of 25. We're going to determine if this adheres to their goal of 77. Okay, so we actually have to put this into a Z formula and figure that out. Okay, so the first thing that we're going to actually do here, this isn't a finite population, so we don't have to necessarily worry about that. But let's find what the standard error of the proportion is. So square root of this times 1 minus this divided by 25. Okay, and then to find our Z here, does 68% fall within the realm of possibilities given this sample? It's 1 standard deviation below the mean, so the probability of this being sort of within that bracket, if you will. Given that it's such a small sample size, it actually, this probability is actually within that realm, because this probability is more than 0.05. So it does essentially provide some evidence that their goal is being reached. So let's see. Yes, because the probability of observing a sample proportion as low as this one in this sample, given a population proportion of 0.77, is, in this case, 0.1425, which is more than 0.05. Okay, and so again, that's you might say, oh, is the thing that we're actually asking is the difference between 0.77 and 0.68 meaningful? Okay, we know it's not, the difference is not equal to 0, but given how small the sample size is, it tends to be that you know, it may not necessarily be, the samples we derive may not necessarily be as accurate. So we're willing to accept some error, and if 0.68, the difference between that and the actual proportion of 0.77 isn't significantly different from 0, is another way of thinking about it, given that the n is 25. Okay, great work on Chapter 7 homework, and keep up all of the work studying and staying up to date with lecture.